Welcome back to the last thermochemistry little clip. And I know this has been a little dry, but I'm very, very proud of you for sticking with this. I really think there'll be a big payoff in the classroom when we have a lot more time to help you work through problems than we typically do. So let's get a start on this. We're given again delta H's of formation. The formation of 1 mole of a substance from its elements in their natural state at standard ambient temperature and pressure. We're going to use these values to find the enthalpy change when nitroglycerin is detonated. Now, I hope you can imagine that when nitroglycerin is detonated, it's going to release a tremendous amount of heat, which means it's exothermic and should have a negative delta H. So that would be our expected value there. Now I like to go ahead and write out the values underneath the substance. So nitroglycerin is minus 364 kilojoules per mole. Nitrogen, 0. Element in its natural state at standard ambient temperature, 0. Minus 393.5 for the CO2. Minus 241.8 for the water, for gaseous water, and it's going to be our products minus the reactants. Always final minus initial, with one exception that you won't come across till we get to AP Chemistry. So delta H for our reaction is, I'm not going to bother with the zeros. It's going to be 12 times CO2s, so minus 393.5. Helps to put it underneath the reaction, I think, so you make sure you grab the right number in the table. Plus 10 times waters. Be careful, because gaseous water is not the same value as liquid water is. Minus 241.8. And then minus 4 times a minus 364 kilojoules. And if we did that mathematics, we get minus 5684 kilojoules. Now that's for the reaction as written. Now if we were to do stoichiometry, that's minus 5684 kilojoules per 10 moles of water, per 12 moles of CO2, or per 4 moles of nitroglycerin, per 6 moles of nitrogen, per 1 mole of oxygen. So we just leave it as kilojoules, and it effectively gives us 1, 2, 3, 4, 5 possible conversion factors. Now the question asks us, what is the change if I have 10 grams of nitroglycerin? So I have 10 grams. This is going to be this many kilojoules for 4 moles of my nitroglycerin, because it's per the balanced reaction, and there's a 4 there. So mass to moles, use molar mass. So I have to go 1 mole per 227.1 gram times minus 5,6. So this is combining what we learned in the stoichiometry part, where we've got the conversion factors for the reaction, and that's minus 62.6 kilojoules for that process. Now there's one more problem to solve, and then we want to focus on application in the classroom. So give that one a shot, give 1418 a shot, pause the video, and don't look at the video until you have tried this problem 1418. So go ahead and pause it if you want to give this a try. Now this time I'm dealing with ammonia, and forming nitric acid is involved. This is actually the first step of a multi-step process. And we want to know, is this an endothermic or exothermic process? So we're going to use these delta H of formation, and we're going to take product sums, and we're going to subtract the sums for the reactants. So delta H of this reaction is 4 times nitrogen monoxides, which is 90, plus 6 times liquid waters, which is given here, minus, well, oxygen is an element, and elements at their natural state at standard ambient temperature and pressure are 0, so I don't have to worry about that. 4 times ammonia's, and ammonia is given as minus 46. Now, it is possible that something like this ammonia was our unknown, and they gave us the heat of the reaction, and then this would be our unknown. I don't have an example here, but I provided some in the homework, because I like you to stretch your application when we get to the homework. If we did that mathematics, we'd get minus 11.72 kilojoules, which means that it's exothermic, which means in turn we'd put heat as the product. And in an energy level diagram, that also means that, the energy of our products is lower than our energy of our reactants. And Mimeo doesn't want to cooperate with me right now, so let's give that another shot. So my energy of my reactants is going to be higher than my energy of my products, and so heat is going to be released in going from one to another. Now remember, the next unit we're going to talk about the fact that there's really a barrier here that we call the activation energy, but we'll get into more details of that later. But that's why combustions require a little spark to get them going. You've done an amazing job. Good luck. I hope that this is enhancing your learning as much as